In this video, we'll understand how RNNs and LSTMs process sequential data like text, speech, and time series. We'll start from the basics of recurrent networks, see why training them is difficult, and then learn how LSTMs solve those problems using gates and memory cells. Along the way, you'll get quick quizzes to check your understanding. Many real-world problems involve sequences, where the order of inputs is very important. In language, the meaning of a word depends on earlier words. In speech and time series too, previous steps influence the next one. That is why we need models that can remember what came before, not just process one input independently. A recurrent neural network, or RNN, is different from a normal feed-forward network because it carries information forward through a hidden state. At each time step, it combines the current input with the previous hidden state. This lets the model build a running summary of the sequence and capture temporal dependencies. From a theoretical point of view, an RNN can be seen as a discrete time dynamical system. That means the hidden state evolves step by step. The future state depends on the current state and the new input. This recursive behavior is exactly what makes RNN suitable for modeling sequences. Now let us look at this in a simple table format. RNN vs LSTM. Core differences in sequence modeling. Here's the main comparison. A standard RNN uses only a hidden state, while an LSTM adds a dedicated cell state for memory. RNNs often struggle with long-term dependencies because of gradient problems, whereas LSTMs reduce this issue through gates. The trade-off is that LSTMs are more complex and usually more computationally heavy. To understand training, we often unroll the RNN through time. In this view, the same network is shown repeatedly for each time step in the sequence. This makes it look like a deep network spread across time, and that is how backpropagation through time, or BPTT, is applied. Now that we've covered RNN basics, let's test what we've learned so far. Here's quiz number 1. See if you can get it right. Question 1. Why are RNNs useful for sequential data? The correct answer is, they keep past information. RNNs maintain a hidden state which helps them use earlier information while processing later steps in a sequence. Question 2. What does the hidden state in an RNN mainly represent? The correct answer is a summary of past inputs. The hidden state acts like memory, carrying information from previous time steps. Question 3. What is the purpose of unrolling an RNN? The correct answer is to visualize time-step copies. Unrolling shows the repeated network across time and helps explain how training works through BPTT. Standard RNNs face a major training problem. When gradients are sent backward through many time steps, they can become extremely small or extremely large. If they vanish, the model cannot learn long-term relationships. If they explode, training becomes unstable and numerically difficult. Because of gradient issues, standard RNNs struggle to learn dependencies over long sequences. Training can also become computationally expensive, especially when the input is large or the sequence is long. So while RNNs are conceptually powerful, in practice they need better mechanisms for memory and stability. This is where LSTM, or long short-term memory, comes in. LSTM is a special kind of RNN designed to remember useful information for longer durations. It introduces a memory cell and a set of gates that control what to keep, what to forget, and what to output. Because of this design, LSTMs are much better at long-range sequence learning. Now that we've covered training and LSTM, let's test what we've learned so far. Here's quiz number 2. See if you can get it right. Question 1. Which problem makes standard RNNs struggle with long-term dependencies? The correct answer is vanishing gradients. Vanishing gradients make the learning signal too weak across many time steps, so long-range dependencies are hard to learn. Question 2. Which LSTM component decides what information to discard? The correct answer is forget gate. The forget gate controls what information from the previous cell state should be removed. Question 3. Compared with standard RNNs, LSTMs are generally. The correct answer is better at long memory. LSTMs are specifically designed to preserve important information over longer sequences. Let's quickly decode the gates. The input gate controls how much new information enters the memory. The forget gate decides what old information should be removed. And the output gate determines how much of the internal memory should influence the hidden state and final output. Together, these gates make information flow much more controlled. During the forward pass, the LSTM calculates gate activations, updates the cell state, and then produces the hidden state. During the backward pass, gradients are propagated through time just like in RNNs, but the gated structure helps regulate the flow. This is one reason LSTMs are more stable during training. The article also discusses advanced LSTM extensions, such as convolutional input context windows, recurrent projection layers, and additional control gates. In real applications, these models have been highly successful in language modeling, speech recognition, machine translation, and sequence generation, like music or video prediction. So the impact is both theoretical and practical. Now that we've covered applications and flow, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. What does the input gate in an LSTM control? The correct answer is how much new information enters. The input gate regulates the amount of fresh information added to the cell state. Question 2. Why is the LSTM cell state important? The correct answer is it acts as long-term memory. The cell state helps preserve useful information across many time steps. Question 3. Which of these is a common application of LSTM networks mentioned in the article? The correct answer is speech recognition. The article highlights speech recognition as one of the major successful applications of LSTM-based models. Nice work! If you understood why unrolling matters, why gradients become a problem, and how LSTM gates manage memory, then you've got the core idea of this topic. Keep going deeper into sequence models because this foundation is very important for modern NLP, speech systems, and generative AI.